Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Dr. Hayden Sharma. Hayden earned his bachelor's and master's degrees from Northwestern University, where he worked on organocatalysis and total synthesis. He subsequently came to Harvard, where he joined the Jacobsen lab and recently completed his PhD, which culminated with some very interesting papers about enantioselective Wagner-Meerwein rearrangements and 1,2-Boronate rearrangements. Currently, he's a postdoc in the Kravit lab at Scripps. And from there, I'll hand the floor over to you, Hayden. Thank you very much for coming on today.
Hello, everyone. Thank you for tuning in, and thank you to Matt for inviting me to share today. I'm very excited to talk about my recently published work on rendering the Madison homologation catalytic and enantioselective. Before I begin, I want to mention that most of this work was done in close collaboration with my lab mate and one-time mentee, Jake Esman, who deserves a lot of credit for what I'm about to share. To begin, boronate rearrangements involve the migration of a ligand from a tetracoordinate boron atom to displace a geminal leaving group. These reactions are SN2-like in nature, as shown in this transition state, as the migration and leaving group displacement occur simultaneously. As a result of this concerted displacement mechanism, these rearrangements feature predictable stereochemical outcomes. For example, these rearrangements are stereoinvertive at the carbon center undergoing substitution, just like canonical SN2 reactions. This stereospecificity is general across classes of migrating groups, leaving groups, and boron ligands, and so is reliably stereospecific for a wide variety of rearrangements, which is sort of different from typical leaving group displacements, which are often not reliably stereospecific, even if SN2-like. Secondly, boronate rearrangements are stereoretentive at the migrating carbon center. This reactivity is what enables a lot of the carbon-boron bond elaboration reactions, such as the classic oxidation with peroxides, where the green ball would be an oxygen and the Lg would be an OH. Before I continue on, I want to define some important terms that may sound similar, but mean relatively different things. You've heard me already mention that boronate rearrangements are stereospecific. Keyword specific. Stereospecific reactions are reactions where, by virtue of the mechanism, one stereoisomer of a reactant produces only one stereoisomer of a product. The canonical example of this is the SN2 reaction. Because the nucleophile approaches from the antibonding orbital of the leaving group, it necessarily flips the stereochemistry of the carbon undergoing displacement. The second term that I'd like to define for us today is stereoselective. Keyword selective. A stereoselective reaction is one where a starting material can form either stereoisomer or product equally, but due to the use of a chiral substrate or chiral catalyst, one stereoisomer is formed preferentially. For example, a chiral catalyst can facilitate an SN1 reaction and control which base of the carbocation undergoes nucleophilic attack to yield just one enantiomer product. I wanted to define these terms because the topic of discussion today is about how to effectively render this class of rearrangements stereoselective, specifically enantioselective. Now, one of the strategies to engender stereoselectivity in reactions that proceed via stereospecific mechanisms is to desymmetrize enantiotopic or diastereotopic groups on the reactant. Rearrangements of boronates bearing two geminal leaving groups can be rendered stereoselective by displacement of one of these stereotopic leaving groups over the other. Particularly useful towards this end are dichloromethylboronates, which feature two stereotopic chlorides, alpha to boron. Upon rearrangement, one of these chlorides is displaced to afford alpha-chlorosubstituted boronic esters. Madison discovered that, by installing chiral diol auxiliaries on the boron, it was possible to control the diastereoselectivity of boronate formation and boronate rearrangement to generate diaster-enriched alpha-chloroboronic esters. These products can then undergo a second metallation and, this time diastereospecific, rearrangement to yield alpha-secondary boronic esters. This process can be conducted iteratively by resubjecting the secondary boronic ester product to dichloromethyllithium, which forms another dichloromethylboronate that rearranges to yield a more complex alpha-chloro compound, which then can be similarly elaborated to enable the synthesis of long stereocomplex alkyl chains. These synthetic efforts typically culminate with an oxidation of the boron with hydrogen peroxide to afford optically active secondary alcohols. There are a few examples also of swapping out the boron for other functional groups, albeit through multi-step sequences. Now, to set up the work that I'm going to be talking about today, I thought that we might be able to use chiral dual hydrogen bond donors to catalyze these types of rearrangements with enantioselectivity. In particular, I hypothesized that the hydrogen bond donor might preferentially abstract one enantiotopic chloride over the other to yield an enantioenriched alpha-chloroboronic ester. I thought that this reaction might be potentially useful for a few reasons. The first reason is that it couples cheap, commercially available or readily accessible starting materials, either organoboron pinacol esters and solvent, DCM, or dichloromethylbpin and organolithiums. The second is that we could use boron pinacol esters, which can be directly diversified into a broad range of molecules bearing new carbon-carbon, carbon-oxygen, carbon-nitrogen, and carbon-halogen substituted stereocenters. Leveraging this, enantioselective catalysis of this reaction might enable a general three-step sequence to construct chiral molecules from dichloromethane, with the first step being enantioselective rearrangement, the second an enantiospecific rearrangement, and the third an enantiospecific carbon-boron bond elaboration. In theory, the ability to modulate any of these latter two coupling partners, signified by the blue and green balls, allows for the programmable construction of an exponentially broad array of stereocenters from one single product of the catalytic reaction. So enough on the pitch, let's put this idea to the test. We first began by looking at the rearrangement of N-butyl substituted boronates with a standard class of chiral thioureas bearing an aryl-pyrrolidine tert-leucine moiety. What we found is that by forming the boronate by addition of N-butyl to DCM-bpin, waiting 5 minutes, and then adding thiourea catalyst, product was formed in 48% EE. It was exciting to know that we could catalyze this reaction with hydrogen bond donors. However, as we continued to screen, we somewhat surprisingly discovered that the product can be formed in higher EE when the reaction is run sloppily by adding thiourea immediately after adding butyl. One interpretation of this is that maybe it's important for thiourea to be present in the reaction flask with butyl. Consistent with this, the highest levels of selectivity were observed when we ran the reaction in a different way, by adding the thiourea even before butyl. While it was evident that we had a somewhat selective hydrogen bond donor catalyzed pathway, there was clearly a much more selective mechanism that was being catalyzed by something other than an HBD. As you might expect, in the reactions where thiourea is present when butyl is added, there is a significant amount of decomposition. Now, we isolated the main decomposition species using para-bromothiourea instead of para-chloro, and characterized it by NMR and mass spec. Now, thanks in part to the unique isotopic labeling patterns, we discerned that the isolated decomposition species consisted of 1 unit of thiourea, 1 unit of DCM-bpin starting material, minus 1 chloride. There are a number of ways that these two things can be combined to lose a chloride, so the structural assignment wasn't clear until we acquired a crystal structure of the species. And this is really where the project took a sharp turn. What we found is that the thiourea sulfur displaces a chloride on starting material, and then the aniline nitrogen attacks the empty p orbital on boron to form a cyclic isothiourea boronate. This species bears a chlorine alpha to the boron, and so we call it chlorocat. I think what's fundamentally cool about this discovery is that there are no previous reports of a carbon stereocenter substituted with a chlorine, sulfur, boron, and hydrogen. Beyond fundamental interest, we wanted to know what impact this decomposition species had on the reaction. When added as a catalyst to preformed boronate, being careful to avoid excess butyl, the product is yielded with low levels of selectivity. However, when we add chlorocat before butyl, we see that the product is formed with very high levels of enantioselectivity. Same as last time, consistent with deprotonation of this species being somehow important. To test this interpretation, we ran the reaction using butyl first conditions, but with chlorocat pre-deprotonated with butyl or lithium HMDS. In these cases, we observed the highest levels of selectivity, consistent with this lithiated chlorocat being the highly active and selective catalyst all along. So now that we knew what was likely mediating these rearrangements, we wanted to get a better picture of the structure and general robustness of this lithiated isothiourea boronate catalyst. We first turned to ReactIR to measure the real-time solution state changes to the catalyst upon lithiation. Two peaks that are easy to monitor on this catalyst correspond to the amide, which has a stretching frequency around 1658 wave numbers, and the isothiourea NCN, which has a stretching frequency around 1596 wave numbers. What we observed is that, upon treatment with lithium HMDS, both of these peaks shift to considerably lower wave numbers. These changes indicate that both of these moieties undergo a change in chemical environment, which would be consistent with a lithiated structure as shown here, where the lithium ion is bound to both the isothiourea and amide to form a 5-membered chelate. Worth noting is that this process is fully reversible upon addition of one equivalent of acid, which gives us confidence that a catalyst is not undergoing some more extreme transformation or decomposition upon deprotonation. Finally, we have the end structure. Okay, so we also wanted to acquire a solid state structure of this species, but tried and failed for a while to crystallize lithiochlorocat. However, we were successful at crystallizing lithiomethylcat, a still catalytically active species that bears a methyl in place of the alpha chloro group. The solid state structure indeed features a chelating lithium ion, shown in pink, placed nicely in the catalyst pocket, corroborating our solution state analysis. Okay, so now that we know what we're dealing with, we wanted to assess the scope of rearrangements that can be catalyzed by these lithium isothiourea boronates. A range of primary boronic esters undergo migration in generally high EE, including substrates bearing modestly Lewis-basic or base-sensitive moieties. However, I will note that substrates bearing more strongly Lewis-basic functionality, such as amides or pyridines, underwent the reaction with either lower EE or didn't give any product. Secondary boronic esters also underwent rearrangement, although only those bearing short or cyclic branching substituents afforded products with high levels of selectivity. Finally, due to the accessibility of isotopically labeled DCM, we were able to make products with deuterium or carbon-13 labeling on the tertiary center. I'll also mention that sp2 substituted boronates can work very selectively in this reaction, but for some reason have very high levels of irreproducibility. After developing the catalytic reaction, we turn to examine the scope of the next step in our proposed 3-step synthesis of tertiary stereocenters. We developed a telescope procedure involving an initial catalytic rearrangement to forward alpha chloro product, which, after a quick aqueous workup, is subjected to an organometallic to displace the remaining chloride to yield a secondary boronic ester. We found that a broad range of carbon-based nucleophiles worked well in the second step, including primary, secondary, sterically constrained tertiary, aryl, and vinyl. These enantiospecific displacements worked also for a broad range of alpha chloro substrates. Additionally, we found that heteroatomic nucleophiles, such as lithium amides, alkoxides, and thiophenolates, could effectively displace that second chloride. One thing that stands out about these displacement reactions is that many of these nucleophiles do not work particularly well in the catalytic reaction, but are highly effective in these non-catalyzed rearrangements. So, for example, if you want a secondary boronic ester with a geminal aryl group or benzyl ether, you can first run the catalytic reaction to install the other substituent you want, and then run a stereospecific rearrangement to install that aryl or oxygen substituent. This highlights the advantage of incorporating robust enantiospecific chemistry in our route to build stereocenters, that the substituents we can use transcend the scope of the catalytic reaction. Additionally, this approach allows for rapid, modular construction of diverse libraries of enantio-rich boronic esters, as each product from the catalytic reaction can easily be elaborated with many different nucleophiles. We then turn to examine the last portion of this 3-step sequence, the carbon-boron bond elaborations. In these reactions, we leverage methodologies initially developed and optimized by Agrawal, Morkin, and a few others. Okay, so homologation yields product 5A, which bears a tertiary carbon stereocenter with all sp3 or hydrogen substitution. Various Zweifel-type olefinations yield sp2 and sp substituted products. Functionalization of alkylboron reagents at the gamma position afforded products bearing fully substituted carbon stereocenters, in the first case by alylation of an imine, and in the second case by this neat stereospecific cross-coupling reaction developed by Morkin. In terms of elaborations to introduce heteroatomic substitution, I hope you're not surprised to know that we can oxidize the boron to an alcohol. But I think it might be of interest to know that the boron to amine transformation proceeds quite smoothly to give chiral alpha secondary amines, which we use to make the somewhat exotic-looking molecule shown here. Taking a step back now, this slide presents the culmination of the developed 3-step sequence, where by modulating each coupling partner along the way, we access molecules bearing a broad range of substituted carbon stereocenters. Now, this is maybe not the best approach to make any individual molecule on here, although I'd argue this is a pretty good synthesis of 5G and 5J, but it is likely the best method to be able to access all of them with one method. That is, I can't think of any other sequence that would enable the enantioselective synthesis of all of these molecules with the same retrosynthetic approach. Okay, so after exploring the synthetic utility of this new boronate rearrangement reaction, we also wanted to figure out what the catalyst might be doing. This is really interesting to us, not just because we're the Jacobsen lab and we do mechanism, but also because there are no other highly enantioselective catalytic homologation reactions like this reported. And so it's unclear in general how to control these very useful reactions. Secondly, there are just a few reports of chiral alkali metal-based catalysts used to mediate other reactions. And so we wanted to figure out how this completely new class of lithium catalyst is working, because it might allow us to delve into the unexplored areas of catalysis in other ways. Our initial hypothesis centered around the catalyst lithium ion, which we reasoned would be a strong Lewis acid that could promote rearrangement through a few different mechanisms, either by direct abstraction of the chloride, or potentially by coordinating the pinnacle of the substrate to free up the substrate lithium to abstract the chloride. To test these basic hypotheses, we turned to the Gutmann-Beckett analysis to assess the Lewis acidity of lithiochlorocat. This technique involves mixing a purported Lewis acid with triethylphosphine oxide, which causes coordination to and polarization of the PO bond that leads to a detectable downfield shift of the phosphorus peak. The change in shift is then plugged into the acceptor number formula, as shown on the slide, which gives the standardized measurement of Lewis acidity that can be compared to other Lewis acids. I found that lithiochlorocat features comparable Lewis acidity to other lithium Lewis acids, as measured here, although is less acidic than traditional strong Lewis acids like titanium or tin tetrachloride. Okay, so we know that the catalyst is Lewis acidic, but there are also quite a few other Lewis acids in the reaction flask, such as lithium chloride or the lithium boronate. And so we reasoned for the catalyst to facilitate the reaction by Lewis acid mechanism alone, it must be a stronger Lewis acid than the other lithium salts. To examine this, we also acquired the acceptor number for lithium boronate substrate mimic that cannot undergo rearrangement. We found that this mimic featured essentially identical Lewis acidity to the catalyst, which rules out catalyst Lewis acidity alone as the explanation for rate enhancement over background. We then turned to DFT analysis, all done by my teammate Jake, to see if we could glean additional insights into the catalyst interactions necessary for catalysis. What we found is that, in the lowest energy transition state leading to the major enantiomer product, the catalyst lithium was indeed bound to the departing chloride, as was also the substrate lithium, which had been coordinated by, and properly positioned by, the catalyst pinacolate and chloride. Comparing this to the minor transition state, only the substrate lithium is proximal to the departing chloride, and the catalyst lithium is unproductively engaged with the non-departing chloride, indicating that both lithium ions are important for abstraction. We've coined this observation that two lithiums are important, sort of cheekily, dual lithium bond donor catalysis, coming full circle from hydrogen bond donor catalysis. Now, I think what's also interesting about this model is that in the major TS, the migrating group is pointing off into space, which explains why we have such broad generality for primary boronates, at least. No functionality interacts with the catalyst, for good or for bad. And actually, the crucial recognition elements, the lithium, pinnacle boronate, and chloride, are universal to all substrates, regardless of what substitution they have. Taking a step more abstract, in this synthetic sequence that we developed, actually, none of the final substituents we install interact with the catalyst. And these latter two substituents aren't even introduced in the catalytic step. This lack of reliance on specific interactions between the catalyst and the terminal substituents we want on our product is what enables the generality of this sequence. And as researchers continue to develop more boronate rearrangement reactions and boron elaboration reactions, these sequences will only increase in generality. In summary, today we discussed the development of a catalytic enantioselective Madison homologation reaction mediated by chiral lithium isothiourea boronates. This reaction serves as the first part in a general three-step sequence that enables the enantioselective construction of a broad variety of tertiary stereocenters, and in some cases, quaternary stereocenters. Mechanistic analysis so far points to the importance of both lithiums in the chloride abstraction step. We're very much looking to the future applications of this work, which splits off in two directions. One of those directions, being headed up by my lab mate and mentee Sam, is the development of a next-generation approach that overcomes a lot of the synthetic limitations of the catalytic reaction to enable more advanced applications. Secondly, we're also exploring applications of this catalyst family to a number of other reactions, some invoking this dual alkali metal mechanism, which is being headed up by Jake and a few others. Alright, so that's all I have today. Thank you for listening, and thank you to Matt for letting me share my work. Please reach out on Twitter or by email if you have any questions.
Thank you for tuning in for this Research Spotlight episode, and thank you to Hayden for sharing your work with us. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.